Chapter 1, Module 2. In this module, we shall formalize the term product of sets. Here, we shall set up a definition for arbitrary product of sets, and for doing so, we shall see that an existential question arises. We call that axiom of choice and discuss axiom of choice in connection with product of infinite sets. We begin with showing that countable product of countable sets need not be countable. For a set capital X, x omega stands for the countable product of x, that is, x omega consists of sequences of the form x1, x2, etc. Each xi are taken from capital X. The theorem says that if X is a set containing 2 points 0 and 1, then the set x omega is uncountable. So, even if we start with a finite set, countable product will give rise to an uncountable set. To prove this, we show that no function from n to x to the power omega is surjective. Suppose G is any map from n to x to the power omega. For any n, suppose G n is equal to the sequence x n 1, x n 2, etc., where these x n i's are either 0 or 1. So, construct an element y n is equal to 1 if x n n is equal to 0 and it is 0 otherwise. Then y n is definitely a member of n, but there is no pre-image of y n under the map G. Hence, G is not surjective as desired. The set 0 1 to the power omega is an uncountable set, giving an example of uncountable sets. We now have another example of uncountable set given by the next theorem. The power set of n denoted by P n is uncountable. For this, it is enough to show that any function g from n to P n is not surjective. For each n, g of n is a subset of n and g of n may or may not contain the point n. So, consider capital M as all those members of n such that n is within n minus g n. Certainly, M is a subset of capital N and thereby a member of power set of n. We claim that M has no pre-image under the map G. For otherwise, let M belonging to n such that G m is equal to capital M. If M belongs to G m, then M belongs to capital M, and therefore, by definition of capital M, M belongs to n minus G m, which is a contradiction. On the other hand, if M does not belong to G m, then M belongs to n minus G m, and hence M belongs to capital M, which is equal to G m, a contradiction. So, we may generalize this result for any set A as follows. There exists no surjective map G from A to the power set of A for any set A. Let us try to prove this result. If A is empty, then power set of A has one element, that is set containing the empty set, and so it is non-empty. Hence, no surjection is possible. Let A not equal to phi. Let G from A to power set of A be any function. Choose any point A from capital A, then GA is a subset of capital A and GA may or may not contain A. We consider the set B as those points of capital A which are lying outside GA. Using a similar argument, we may then conclude that B has no pre-image in A under the map G. Now we define Cartesian product of two sets. Suppose we take two sets A and B. Cartesian product of A and B, denoted by A cross B, is the collection of all points x, y, the pair, such that x is taken from capital A and y is taken from capital B. So, any element of the product of n many sets looks like an ordered n tuple. But the problem arises when we want to define infinite product of sets, because the concept of ordered n tuple is no longer valid for the infinite case. However, the idea of finite product can be generalized for taking product of countably many sets, where each element may look like a sequence. In finite case, an element is of the form x1, x2, xn, an n tuple where xi's are varying over capital Xi. So, intuitively for countable case, an element should look like x1, x2, etc., a sequence where each xi is taken from capital Xi. As we know that a sequence is a function from the natural numbers to union of capital Xi, we may rewrite this element x1, x2, etc., as a sequence x from n to union xi, I varying over n, such that xi is equal to x suffix I, which is a member of capital Xi. With this, we define countable product of sets as follows. Capital Xi, I varying over the natural numbers, be a countable collection of sets. These xi's may or may not be disjoint. We define the Cartesian product of this family of sets, which we denote by product xi, by the set of all functions from n to union xi, such that x suffix I is the element xi, that is the image of the natural number I under the map x, which should be lying inside capital Xi. Each element x is denoted by xi within bracket, I varying over the set of natural numbers, and the set capital Xi is called the ith factor of the Cartesian product. We first establish a result that finite product of countable sets is countable. Previously, we have seen that countable product of countable sets need not be countable, but now we show that the result is true provided we take finite product. So, we start with two countable sets A and B. There are two possibilities. one is either A or B is empty, and the second possibility is that both of them are non-empty. So, if one of them is empty, then the product is empty and therefore, the result is true. Therefore, without loss of generality, we assume that both A and B are non-empty. There are surjective functions f from n to A and g from n to B, as they are non-empty countable sets. We define a function h from n cross n to A cross B by h n m is equal to the pair f n comma g m for any A B belonging to A cross B. As f and g are surjective, there exists n and m in the set of natural numbers such that f n is equal to A and g m is equal to B. Consequently, the pair A B is equal to the pair f n comma g m and thereby equal to h of n m, that is h is surjective. On the other hand, there exists a bijection eta from n to n cross n. So, combining these two, we have a surjection h composed eta from n to A cross B, proving that A cross B is countable. The description of countable product inspires us to replace the set n by any arbitrary index set and achieve the definition of product of any arbitrary collection of sets. So, replacing the set n by any arbitrary index set lambda, we get the definition of product of any number of sets, that is a collection x alpha, where alpha is varying over the index set lambda, and we define exactly the way we had defined for countable products and get a definition for arbitrary product, and each x alpha is called alphath factor of the Cartesian product. If we take product of finitely many finite sets, then we have seen that if the sets are non-empty, then the product is also non-empty, and that is very easy to understand thing. But if we replace the product by infinite product and sets by infinite sets, then can we expect the same thing to happen? Unfortunately, this will not be the case unless we assume something which is known as axiom of choice. So, let us discuss the axiom of choice in the next section. If X is the Cartesian product of a family of sets x alpha, then P alpha from the product X to the alphath factor x alpha given by the point x alpha, alpha belonging to lambda is mapped to the point x alpha is called the alphath projection map. If a finite family of non-empty sets x1, x2, xn is taken, we can easily prove that if each xi is non-empty, then the product xi I equal to 1 to n is non-empty. And secondly, the ith projection map Pi is surjective. The validity of the results for arbitrary products depend on axiom of choice. The axiom states that given any non-empty family A alpha, alpha belonging to lambda, of non-empty pairwise disjoint sets, there exists a set S consisting of exactly one element from each A alpha. If the non-empty family is a finite family, then the statement of axiom of choice is obvious and easy to understand. But in case of infinite, this obvious looking statement plays pivotal role. Absence of axiom of choice results in failure of a plenty of nice results. We see that the following statements are equivalent. If we take a non-empty family of sets A alpha, alpha belonging to lambda, and we know that each A alpha is non-empty, then their product is non-empty. This particular statement is equivalent to axiom of choice, and it is again equivalent to the last one, that is, if a non-empty family of non-empty sets A alpha, which are not necessarily pairwise disjoint, there exists a map C from the index set lambda to the union A alpha such that for all alpha, corresponding C alpha is in capital A alpha. The function C is called a choice function for the family A alpha. Let us try to prove these equivalence conditions. We show 1 implies 2. Suppose A alpha is a non-empty pairwise disjoint collection of sets. Since A alpha is non-empty by 1, the product A alpha is also non-empty. Hence, there exists some A alpha in the product, and we choose capital S as all the points A alpha, alpha varying over lambda. Then S satisfies the requirement of axiom of choice. 2 implies 3. Suppose A alpha is a non-empty family of non-empty sets. For each alpha, choose B alpha as the Cartesian product singleton alpha cross A alpha, then B alpha is non-empty. Also B alpha intersection B beta is empty whenever alpha not equal to beta. Hence, by axiom of choice, there exists a set S containing exactly one member from each B alpha. That is, there exists a unique pair alpha A alpha inside capital S such that A alpha is inside capital A alpha. Therefore, a function C from lambda to union A alpha can be defined by C alpha equal to A alpha whenever alpha A alpha is in S. This proves the existence of choice function. Now, 3 implies 1. If C is a choice function, that means a function from lambda to union A alpha, then by definition of arbitrary product of sets, C must be a member of the product A alpha, and that proves the product A alpha is non-empty. Now, we observe how axiom of choice is assumed in the proof of the following theorem. We take a collection A alpha, alpha belonging to lambda, of family of non-empty sets. If delta is a subcollection of lambda and P is a function from the product A alpha where alpha varies inside the set lambda to the product A alpha where alpha is varying over the set delta is defined by P A is equal to A restricted to delta. Then P is a surjective map. Suppose x alpha is a point, we denote the point x alpha by x. The point is taken from product of A alpha, alpha belonging to delta. We have to find some element A in the product A alpha, alpha belonging to lambda such that P of A is equal to x. As x is a point in the product A alpha, alpha belonging to lambda, for each alpha belonging to lambda, we have x alpha inside A alpha. Since A alpha, alpha belonging to lambda minus delta is a non-empty collection of non-empty sets, there exists a choice function C bar from lambda minus delta to the product A alpha, alpha varying over lambda minus delta such that C bar of alpha is inside A alpha for each alpha belonging to lambda minus delta. So, define A from lambda to the product A alpha by A of alpha is equal to C bar alpha when alpha is inside the set lambda minus delta and A alpha is equal to x alpha when alpha is inside the set delta. Then A belongs to the product A alpha and of course, P evaluated at the point A is equal to A restricted to delta and that is equal to the small x. Hence, P is surjective. As a corollary to this theorem, we get that the projection maps are all surjective. So, we see that if we can prove this corollary, actually we are assuming axiom of choice to get this result. Choose delta to be the singleton beta, then by the theorem P beta is equal to the function P from the product A alpha to A beta and it is surjective and that proves the result. In the next corollary, if A alpha is contained in B alpha, then the product A alpha will be contained in product B alpha. Conversely, if each A alpha is non-empty and the product of A alpha is contained in product of B alpha, then A alpha should be contained in B alpha. Now, if A alpha is contained in B alpha, then it is trivially true that the product A alpha will be contained in product B alpha. And for the converse, we can rely on the previous corollary. In mathematics, we frequently use the principle of recursion. We shall now establish the validity of such principle in this module. Let us define what we mean by recursion. Suppose capital A is a set and A0 is a point in capital A. Let C be a collection of functions defined on sets of the form 1 to n for each n belonging to the natural numbers into capital A, and psi is a function from that collection C to the set A. A function h from n to a is called a recursion if the following holds: h1 is equal to a0 and hi is equal to psi of h restricted to 1 to I minus 1 for all I greater than 1. The following are a couple of examples of recursion. Suppose a is the set of real numbers and a0 is a point in R. Then h from n to R defined as hn is equal to a to the power n is a recursion, because if we define psi by psi f is equal to fm multiplied with a0, where f is a function from the section of natural numbers 1 to m to R, then we have h1 is equal to a0, h2 is equal to psi of h restricted to a1, which is equal to h1 times a0, and that is equal to a0 square. Similarly, h3 will come out as a0 cube, and hence for any I greater than 1, we have hi is equal to a0 to the power of I. Next is another example where we take a as the set of real numbers, a1 is a point from R, and for a sequence a1, a2, an of real numbers, we define a function h from n to R by hi is equal to a1, a2 etc. up to ai, this product. Then h is again a recursion, because if we define psi by psi f is equal to fm into a m plus 1, where f is a function from the section 1 to m to R, then we see that h1 is a1, hi is the product a1, a2, ai, and this holds for all I greater than 1. For what follows, we assume that capital A is a set, a0 is a point from capital A, C is the collection of functions defined on sets of the form 1 to n for each n belonging to n into the set A, and psi from C to A is a well defined function. We shall show that for any n belonging to the natural numbers, there exists a function f from the section 1 to n to the set A satisfying f1 equal to a0 and fi is equal to psi of f restricted to 1 to I minus 1 for all I greater than 1. We prove this result by induction on n. Let n is equal to 1. Then define f from 1 to a by f1 is equal to a0, which shows that the result is true for n equal to 1. Suppose the result is true for n minus 1. So, there exists a function g from 1 to n minus 1 to capital A such that g1 is equal to a0 and gi is equal to psi of h restricted to 1 to I minus 1 with I greater than 1. Define f from 1 to n to the set A by fi is equal to gi when I is 1, 2 etc. up to n minus 1, and fi is equal to psi g when I is equal to n. Then this f is the desired function. In the next lemma, we start with two functions f and g. The first one is defined on the set 1 to n and the second one is defined on the set 1 to m, and both are mapping inside capital A such that f1 is equal to g1 and that is equal to a0, a particular point of capital A. Fi is equal to psi of f restricted to 1 to I minus 1 and gi is equal to psi of g restricted to 1 to I minus 1 for all I greater than 1. then the result says that if I is equal to Gi for all I belonging to the domain of F intersection domain of G. If possible, let there is some I in the intersection domain F and domain G such that Fi is not equal to Gi. Then certainly I not equal to 1, because by the hypothesis F1 is equal to G1. Without loss of generality, assume that I is the least positive integer such that Fi not equal to Gi. Therefore, for all j less than I, Fj is equal to Gj holds. That is, F restricted to 1 to I minus 1 is equal to G restricted to 1 to I minus 1, and consequently Fi is equal to Gi, which is a contradiction to our assumption. Now we state the principle of recursion. It says that if we start with a set A and a point A0 from A, and if C is a collection of functions defined on the initial segments of the natural numbers to A, and psi is a well defined function from C to A, then there exists a unique H from N to A such that the condition for recursion holds. That means there exists a unique recursion H. First we prove the existence of such H. Let us consider Fn from 1 to n, the initial segment of the natural numbers, to A, satisfying the conditions that Fn1 is equal to A0 and Fni is equal to psi of Fn restricted to 1 to I minus 1 for all I greater than 1. Then the first lemma guarantees the existence of such functions Fn for each n belonging to n, and by second lemma, if I is in the intersection domain Fn intersection domain Fm, then Fni should be equal to Fmi. Hence, we have a function h from n to a given by h1 is equal to a0 and hi is equal to Fni for all I greater than 1. Now, to prove the uniqueness of H, if possible, let there be some k satisfying the same condition, then clearly H1 is equal to k1. Now, for H not equal to k, there exists some positive integer, and we suppose that is the least positive integer I, such that hi is not equal to ki. Now, why we are saying so? That it is known that least positive integer exists by well ordering principle of natural numbers. In such case, for all j less than I, Hj is equal to Kj, and now for Hi is equal to psi h restricted to 1 to I minus 1, and that is k restricted to 1 to I minus 1, which is Ki, which gives rise to a contradiction to our assumption that Hi is not equal to Ki, and that proves the uniqueness of the function h. To sum up, we have introduced product of arbitrary family of sets, and we have discussed and shown the validity of use of principle of recursion in throughout mathematics. With this, we end chapter 1, module 2.